Chem 201, College Chemistry 1, Chapter 9, Covalent Bonding Orbitals. Here we complete what we started on Chapter 8 about the theory of bonding. Right? So in Chapter 8, we were seeing like how atoms were forming a chemical bond, the polarity, molecular geometry, which is very crucial to form a chemical bond between two atoms. In this case, we will see a particular section which is about covalent bonding. And so orbitals, there are some strategies, as we will see later on, that the atoms have to maximize their bonding or to make it more stable. I have shortened the chapter 9, so we're not covering every section, so we're only focusing on these 4 sections. My main focus is going to be hybridization and molecular orbitals, as you can see here. Right? So we will see some specific cases for homonuclear and heteronuclear diatomic molecules, but they are all under the umbrella of the molecular orbital model. Right? So the MO, as we know this model, is about like how do orbitals in 2 different elements combine to form a covalent bonding. Okay? So let's start by hybridization, which is a concept that is very important for the ones that are taking organic chemistry. Also, this word is going to be repeated many times in organic chemistry. Okay? So draw the Lewis structure of methane, CH4. So we have done that before, right? So it is a tetrahedral molecule because we have here CH4. Carbon has four bonds. Well, we know that carbon has 4 valence electrons. It has 4 valence electrons, and then we know that hydrogen also has 1 valence electron. So 1 valence electron will match with the valence electron of carbon. So we will have a molecule like this, CH4, a carbon as a central atom with 4 hydrogens. So 4 electron groups, 0 lone pairs. The geometry is tetrahedral, which is exactly what we see here. The shape of the molecule is going to be tetrahedral. What are the bond angles? The bond angle is 109.5 degrees. And so here is the molecule. So this is what we have for the conventional procedure that we did on chapter 8. But there are in some cases, there is a phenomenon that occurs, which is called hybridization, as we will see. Because you might say like, okay, well, how do we know that this is tetrahedral? As far as I know, carbon is S2, P should be P2, right? So that would be the valence electrons for carbon, right? Because it's atomic number 6. So 1s2, 2s2, 2p2. So you might say like, well, why is it tetrahedral? I thought that s orbital is spherical and p orbitals are like this shape, right? Like they look like 2 balloons. If I have P2, that means that I'm using two p orbitals, which will look like this. So the center will be the s orbital right here, and then we have 2 p orbitals, right? So each of them are, they are perpendicular to each other. So how can I get a tetrahedral shape with these orbitals, right? Because we know that s has this particular shape and the p orbital has this particular shape, more or less, right? So how can I have 109 degrees? Apparently they look like they are 90 degrees apart, right? So at least the p orbitals are 90 degrees apart. So that's what completes or why is that, how come that geometry comes up, right? So that's exactly the deduction, the hypothesis. Like if we have S2P2, why can the bonding orbital for methane be formed by overlapping atomic orbitals? Well, the bonding in methane, it had to be explained how come it gets a tetrahedral shape when all the orbitals are perpendicular. So hybridization, that's how they explain it, through hybridization, which by definition is the mixing. It's a property that some atoms have, that they have the property of mixing a native or a natural, right? A natural orbital, atomic orbital, to form a special orbitals for bonding. So not every atom is going to be hybridizing. So the main purpose of hybridization is that if an atom is going to form a bond, if you're not going to form a bond, so no hybridization will occur. So hybridization only occurs if a particular atom decides to bond. Are they all going to make this hybridization? No, not all of them. Mostly happens with the small atoms, right? So doesn't mean that the large atoms are not going to do it. These large atoms also hybridize, but is only more occurring in smaller atoms. Why? Because remember, the smaller atoms, the orbitals are closer to the nucleus. So remember that the electrons want to get away from the nucleus because the nucleus is positive, minus and positive they will attract. So they don't want to be at risk of being attracted to the nucleus. So the electrons tend to maximize their separation, not only to get away from the nucleus, but also to avoid electron-electron repulsion. Because 90 degrees apart is not the most efficient, right? 90 degrees apart is, it's perpendicular is 90 degrees. Tetrahedral, 109 degrees. So the electrons go from a separation of 90 to 109 in the case of tetrahedral. So sp3 hybridization is the combination of 1 and 3 p orbitals. And for this, I would say that that's better if I explain it with on the paper. Okay. So here what we have, at least for carbon, right? So we know that carbon is atomic number 6. So the electron configuration is 1s2, 2s2, 2p2, right? So the valence electrons, remember there's always the outermost shell. So we have the 2s orbital, and also we have the 2p orbital. But in p orbitals, we have 3 orbitals. In the p subshell, we have 3 orbitals. The s has only 1. So according to this, we have 1, 2 electrons, and then 2 p orbitals, so 1 and 2. So theoretically, the carbon atom will have the s orbital in the center, and then it has the 3 p orbitals, right? The 3 p orbital here, let's say this one is px, this one will be py, and there is a third one which could be, let's call it pz, right? So it's 3 orbitals that we have. Okay? So the central is the 2s, then here is px, right? 2px, here is 2py, and 2pz. Okay, so it doesn't, it is just a convention to write these 3 axes. The pz can be the vertical, the horizontal can be the x, and the y doesn't really matter as long as you have all of them are perpendicular. Okay, so from this one, we have that 2 electrons are here. So 2 electrons should be here, and then 1 electron in x and 1 electron in y. What happens in z? Well, z is empty, right? Because there is no electrons on this orbital. This is empty. So you can see the electrons, they are not the most separated, right? So this electron is 90 degrees apart, and also the central electrons, which are the valence electrons, right, that are also concentrated very close to the nucleus. So that is bad for the electrons, right? First of all, because this electron might encounter those 2 electrons, this electron can also encounter those 2 electrons. And also the separation between these 2 electrons is 90 degrees. So it's not the most optimal. So what happens in hybridization? When we hybridize, the purpose of hybridization is to maximize the separation and also reduce energy of the electron, right? Because that proximity of the electrons generates instability or increases the energy, higher energy. We want to bring that down, bring the energy down. How can I bring it down? By doing hybridization. If the atom hybridizes, it will lower the energy of the electron. Okay? So what it's going to do, I'll just give you a brief of what happens. You have 1 s orbital and you have 3 p orbitals. The highest hybridization is called sp3. Why is it called sp3? Because it combines 1 s orbital with 3 p orbitals. So you're going to combine everything. So you will form, right? So how many atomic orbitals are you mixing? This is an atomic orbital for 2s, atomic orbital 2px, atomic orbital 2py, atomic orbital 2pz. If you mix them all, you're mixing 3 atomic orbitals. If you hybridize 4 atomic orbitals, you should also get 4 hybrid orbitals. So you will have an sp3, 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 and sp3. You will form 4 atomic orbitals, hybrid orbitals, called all sp3. Okay, so now if you complete the electrons, how many electrons? 4, 1, 2, 3, and 4. So you have 4 ampere electrons now for carbon. That's why, the valence electron for carbon is 4, right? Because you have 4 ampere electrons. So each of them is able to form a covalent bond, right? That is the highest, right? So now what happened with the next one? So let's do again the 2s, 2px, py, and pz, right? So that's another case. It's the same atom, 2s with the orbitals. Now, I don't want to mix them all. because in sp3 hybridization, I mix all of them, right? The 1s, I mean the single s, I mean this s, and then the 3 p's. But do I have to mix them all? No, not necessarily. In the second hybridization, what you will do, you will only mix the s with the p's, okay? 2 p's. So you will get what we call the sp2 hybridization. Why is it called sp2? Because you're mixing the s with 2 p's. So you will get how many? You're mixing 3 atomic orbitals, then you will form also 3 hybrid orbitals. Here I form 4 hybrid orbitals. But in this case, I will only get 3 hybrid orbitals. What happens with this single PZ that I didn't mix? Well, you will just get a pure p orbital. You didn't touch that, so you should get that, okay? So in the sp3 hybridization, you get 4 hybrids, 0 p's, no p's, okay? No p orbitals. In the sp2 hybridization, you only mix 2 of them, 2 p's and the s. Then since you're mixing 3 orbitals, you also get 3 hybrids. But that unhybridized or untouched PZ, you get it. Oh, do I have to hybridize always X and Y? Can I hybridize Z and X or X and Y, Y and Z? Yes, doesn't matter. I mean, again, this is a convention. You don't have to be PZ. This pure p orbital can be PZ, PX, PY, okay? Next one, the second, the last type of hybridization, 2s, and then we have the PX, PY, and PZ, right? Now, I don't want to hybridize 2 p orbitals. Now I want to hybridize 1 p orbital only. Then in this case, I'm hybridizing an s and a p. Then the hybrid I will get is sp. So this is called the sp hybridization. How many atomic orbitals are we mixing? We're mixing 2 atomic orbitals. Therefore, you're also going to get 2 hybrid orbitals. So this is 3 hybrid orbitals and 1 pure p orbital. Here, I get 2 hybrid orbitals. And how many pure p orbitals? Well, this one I didn't touch, this one I didn't touch. Then I will get py in this case and pz. I get these 2 pure p orbitals. That's what happens in the sp hybridization. What is the shape of this, or what? How do I know that I have to use sp3? How do I know that I have to do sp2? How do I know that I have to do sp? It depends on the number of bonds that the atom is forming. Okay? So for example, in this sp3 hybridization, you can see that you can form 4 bonds. So if you have an atom that needs to form 4 bonds, 4 separate bonds, then you will use sp3. If you see that the atom is forming 3 bonds only, right? 3 bonds, because the hybrids are the ones that really are responsible for bonding. So then I will use sp2. If my atom is only forming 2 bonds, is sp, right? So one quick example, CH4. CH4, I have CH4. I can see here that carbon is forming 4 bonds. So 4 bonds, the hybridization that allows me to form 4 bonds is sp3. And that's correct. Methane is sp3 hybridization. What about in sp2? One example for sp2. Right? In this case, how many bonds is this carbon forming? This carbon is forming 3 bonds, right? 1 double bond and 2 single bonds. Oh, but the double bond doesn't count as twice? No, this is a double bond. It's just 1 single bond. I mean, it is 1 single type of bonding. It happens to be double bond, but you don't count it as twice. It's only 1 bond here, 1 double bond, 1 single bond, 1 single bond. How many bonding? 3 bondings, right? So it's 3 branches. Let's call it like that, 3 branches. What hybridization allows me to do 3 branches? sp2, because you do the branches with the hybrids. Okay? In this case, I had 4 branches. So who allows me to do 4 branches? sp3. One example for sp. So now this is another case. They ask me, what is the hybridization of this carbon, right? So how many bonds are coming out of carbon? In this case, I see 2 bonds, 1 single and 1 triple. So what hybridization allows me to do 2 bonds is the 2sp. Can I use sp3 here or sp2? No, because it's depends on the type of bonding. Here you need to form two bondings, right? One single and one triple. Again, once again, the bonding is not counting by the multiplicity. It can be double, single, or triple. So whichever is the type of bonding, but it is a type of bonding, so it only counts as once, right? So two bonds, right? One single, one triple, that means that it's sp2. So then what is the effect of the p's, right? So what is this pc and this pypc? So what would be the effect, right? Because there should be a reason, right? Because right now we're describing all these atoms based on the number of hybrids. But what is the purpose, right? What is the purpose for these pure p orbitals? Those pure p orbitals are actually crucial because this bonding, right, this one that I'm labeling in red, these are actually going to be the pure p orbitals. Right. So this red bond right here is really coming from the PZ. And here, these other red bonds here are coming from the PY and BZ. I mean, here I will go into the details for this particular, how this occurs in each of the cases that we will have for the bonding, right? So let's go here. In the case of the sp3 hybridization, we combine one s orbital and three p orbitals, all right? So whenever a self-equivalent tetrahedral atomic orbital is required by an atom, the localized electromodel assumes that the atom adopts a set of sp3 orbitals. Then the atom becomes sp3 hybridized, right? So whenever you need a tetrahedral atom, right, which maximizes the separation of 4 different groups, that's when you will bring up the sp3 hybridization. Okay? So this is very similar to what we were explaining, right? So we have the 2s, and you have the 3p's, the 3p orbitals to hybridize, and you form the 4 sp3 hybrids. So this is the geometry. So this is the geometry of the s orbital. Like we were saying, it was spherical. The p orbitals are these lobes, right? Has this lobular geometry. Once they hybridize, they form, this is the shape of the hybrids. This is sp3 hybrid 1, sp3 hybrid 2, sp3 hybrid 3, and sp3 hybrid 4. So remember, you form 4 hybrids because you're mixing four atomic orbitals. Therefore, you also form 4 hybrids. How are they disposed, right? In the element, I mean the carbon element in this case. So the 4 orbitals could be right here. So you see the 4 orbitals, 4 sp3 orbitals. Okay, that's the tetrahedral set for 4 sp3 orbitals. That's, for example, methane. That's how you come up with the geometry of tetrahedral geometry, right? With an sp3 hybridization. The H does not hybridize because the H is too small, has only 1 orbital. So when hydrogen hybridize, I mean, it's impossible for hydrogen to hybridize. To hybridize, you need at least to combine or to blend 2 different orbitals, right? So you cannot blend 1s with another 1s. No, that doesn't, it cannot be, that's not possible. You have to do hybridization with different orbitals, in this case, s and p. Okay? Draw the Lewis structure for ethylene, C2H4. So here is the geometry, here is the ethylene. I mean, we have done this already in chapter 8, that's why I'm skipping the procedure part. So the ethylene, you can see that this one is the geometry for this carbon is trigonal planar. Trigonal planar because it has 3 electron groups, 0 lone pairs. 3 electron groups with 0 lone pairs, that is a trigonal planar geometry. The bond angle is 120 degrees because it's a triangle, right? So how can I have that? I mean, that question comes back, right? So I know that the s orbital is spherical. The p orbitals are perpendicular, meaning 90 degrees. How can you get 120 if you have 90 and then spherical, right? So the reason or what happens in this case now, it is that you cannot use sp3 hybridization. right? Why can you use sp3 hybridization? Because in this particular case, remember, sp3 allows you to have 4 bondings, right? So in the case of ethylene, you don't have 4 bondings, right? You have only 3. Where are the 3 bondings? Here, this single bond, and then this double bond. So it's 3 bondings. So you cannot have 4 bondings, right? A 4 bonding system to have only 3 bonding. What is the system that allows me to have 3 bondings? Well, sp2. Okay, so sp2 then is the one that it will use now 1s orbital. It always involves the 1s orbital, right? So there is no way to avoid it. So some students might ask, oh, what about if I don't hybridize the s and I hybridize all p's? Can that be possible? No. Your hybridization always have to mix more than one. At least 2 orbitals, 2 different orbitals can have to be mixed, meaning the s and the p. Can I also hybridize sp and d? Yes, you can also do sp and d. It is part also in the book, in this chapter, you have another type of hybridization that they mix sp and d's, but we are not doing that. I mean, I'm focusing mostly in the material that you guys will need for the future, for the near future, which is organic. In organic chemistry, the most common hybridization you will be seeing is sp2, sp3, and sp. That's why I'm emphasizing in this CHE201 class, those hybridizations. The other SPD hybridizations, right, that come with atoms that are larger, they are more common, but in inorganic chemistry. Inorganic chemistry is normally taken by chemistry majors, but that is a specific course for that. So anyway, you will take it later on. But just by knowing the concept of sp2, sp3, and sp hybridization, you will know all the hybridization because they all work the same way. Okay, so coming back to this sp2 hybridization, you have 1 pure p orbital and 1 pure s orbital and 2 p orbitals. It gives a trigonal planar arrangement, and 1 p orbital is not used, right? The same way as I was explaining on my write-up with my camera. Okay, so they are perpendicular electron pair between the atom. Oh, here, very important. What is a sigma bond? What is a pi bond? That's exactly what I was telling you with the bonds in red, the bonds with a pencil. Okay, so a sigma bond is an electron pair that is shared in an area centered on a line running between 2 atoms. A better explanation for a sigma bond is a type of chemical bond or a covalent bonding that is formed by a complete overlap of 2 atomic orbitals. When 2 atomic orbitals physically overlap, that's when you're in front of a sigma bond. Okay? So I can explain you this with the camera. Okay? So let's say in the case of methane, in methane, right, you have CH4. This one is called a sigma bond. Okay? Is the Greek letter sigma? Sigma bond. What happened in the other case when I was telling you, here you have a double bond. A double bond, one of them is the sigma bond, and the other one is called the pi bond. Does it have to be the right and the left, sigma and pi? No, doesn't matter. In a double bond, one of them has to be, doesn't matter which one, has to be the sigma bond, the other one has to be the pi bond. What in the triple bond? The triple bond, one of them is the sigma, doesn't matter which one. Again, doesn't matter if it's the middle, the top, the bottom one. One has to be the sigma. The other 2 are going to be the pi. Pi 1 and pi 2. Does it matter which one is pi 1? No, doesn't matter which one is pi 1, pi 2. The 3 bonds have to be distributed, 1 sigma and then 2 pi's. Okay? So that's how it works. So what is the difference between a sigma and a pi bond? A sigma, I think it's a good timing for the sigma. The sigma, let's say that you have the sp3 hybridization. Okay? So these are my 4 sp3 hybrids, and they form a covalent bond with hydrogen. Hydrogen is sp, therefore sp is s orbital, and this one is an sp3, right? Each of them is an sp3. This is also an sp3. So the carbon with the 4 sp3s, right? Each of them is going to form a chemical bond with hydrogen, which is s orbital. This physical overlap, this intersection right here, that is what we call the sigma bond. There is a physical overlap between the 2 orbitals. they touch to each other, they're holding hands. That's what we call a sigma bond. What happens in a pi bond? I'll show you what happens in a pi bond. Remember, a pi bond has to be at sp2 hybridization. You cannot form pi bonds, right, with sp3. sp3 does not allow you to form pi bonds. To form pi bonds, you need sp2 or sp. Why? Because to form pi bonds, you need pure p orbitals. Who allows you to have pure p orbitals? Well, the ones that allow me to have pure p orbitals are sp2, right? Because sp2 has one pure p orbital, and sp. sp has two pure p orbitals. So in the case of pure p's, I will have sp2 and sp hybridization. Okay, so if I want to do an sp2, okay, so that is my carbon in sp2, 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 right? 3 sp2 orbitals, right? Because remember that hybridization forms 3 hybrids. Let's do this one, HH. Each of the carbons, each hydrogen will bond to the, right? Each bond will bond to the, I should have written it this way. Here. Okay. The hydrogen has the two here forms a pi bond, sorry, sigma bond here. Here, who is here? Well, I have C double O. So that means that here the oxygen, here oxygen is also sp2. Don't worry about the sp2 or the oxygen. Right now, let's focus on the carbon. The carbon is my sp2, okay? So here the carbon has the 3 hybrids, but it's sp2. That means that this carbon also has a pure p orbital. Oh, how do you come up with that? Well, remember, sp2 hybridization coexists with one pure p orbital. Where is this pure p orbital? That pure p orbital is right here. Where are the 3 sp2s? 1, 2, 3, 3 p sp2s, and then the pure p orbital. Okay. The oxygen is similar, it's the same thing. So it will also have a pure p orbital. Right? Here you have electron. Well, here is the sigma bond between the oxygen and the carbon. Where is that sigma bond? Well, that sigma bond is right here. Here, this CH is this CH. This CH is this CH. This one is the CO sigma. That CO sigma is right here. Who is this? This is the pi, right? This is the CO pi. What is the CO pi? The CO pi comes from the interaction between the p orbitals. The pure p orbitals interact to each other. What is the main difference between a sigma and a pi, right? They look the same, right? It's a bond between oxygen and carbon. The difference, you can tell the difference from this diagram. The sigma bond is a physical overlap. So they are touching to each other. They are holding to each other. What happens in a pi? In a pi, you don't have a physical overlap. These two p orbitals are not touching each other. They are just face to face, kind of like through a space. It's a through a space interaction. It's only that the electron here, let's say, is pointing up and the electron here is pointing down. So how is this attraction? This attraction is basically magnetic. One is a spin plus 1/2 and the other one has a spin minus 1/2. That's how they interact. So the pi bond is also a covalent bond, but it is through a space. There is no physical interaction between the atoms or the atomic orbitals to form the pi bond. For the sigma bond, you do. The sigma bond, you cannot have a sigma between a physical interaction. The sigma exists. This one is also sigma. This is sigma. So some of you might say like, oh, what happened with these orbitals in oxygen? Who is there? Well, I didn't write it completely, right? But oxygen has 2 lone pairs of electrons. So in this case, you will have 2 electrons here and 2 electrons there. Okay? So we'll go over this, later on the slides, but I think this one was a good timing for me to explain you what is the difference between a sigma bond and a pi bond. So sigma bond is the physical interaction between 2 atomic orbitals. hybrid or not hybrid. For example, in this case, hydrogen is not hybrid. It's not hybridized. Here, this one is hybridized. So the interaction can be between unhybridized or hybridized. But the idea is that they have to be a physical contact, physical contact point. Here also a sigma. See, here is a sigma between two hybridized orbitals. Oxygen here is also sp2. So here is a sigma bond formed by two hybrid orbitals. This one is a sigma bond between a hybridized and a non-hybridized orbital. The hydrogen is not hybridized. Okay? So that's the sigma. It's a physical interaction. The pi, no. The pi is a through space interaction between two orbitals. In this case, the pure orbitals are the ones that are responsible for the pi bond. Okay? Do they have to be face to face? Yeah, of course. Right? If you're going to form a bond with another element, right, with atomic orbital, it has to be on the same face. It has to be looking at each other like this. You cannot form a sigma bond like this. There is no pi bond like that. If you form a pi like this through space, but face to face. You cannot form a pi like this or like this. No, there is no pi. If you form a pi, it has to be the same distance. That means that, the same phase. That means that the pi bond can only be formed if these two guys are the same axis. If this one is a px, this one also has to be a px. You can never form a pi bond if you change this. Like, for example, px and py. No, you cannot have a pi there. Or what about a pz and a py? No, it has to be the same. Py, pz, pz, px, px. They have to be the same. Why did you write px? Why didn't you write py or pz? That doesn't matter. Remember, the hybridization creates one pure p orbital. That pure p orbital can be px, py, pz. You designate it, you name it. Right? So, but the most important thing is that they must be the same phase or the same axis. Right? Px with px, py, py, pz, pz. Okay? Because they have different angles, right? Remember, they are 90 degrees apart, right? Px, py, and pz. Okay, so let's continue with the slides. We went over sigma bond, pi bond forms double and triple bonds by sharing electrons in the space above and below this sigma bond. Yeah, what do we mean by above and below the sigma bond? Yeah, that's exactly what we see. This is the sigma bond, and the pi bond is above and below because that's the p orbital, right? The p orbital is above and below the sigma. The sigma is the axis, right? It's like the connection. It's the skeleton. And around that is where the pi bond will be, right? Will be formed. It's really like a cylinder. This is a cylinder. Okay? It's a very complicated system. The bonding, but the idea is that the sigma is always internal, and the pi is the one that is external. Is in the surrounding. It's like a cylinder, right? So imagine like a finger, and then I have a cylinder, right? It's like a pen. And then this is the sigma bond, and the pi is going to be like this, right? So the pi is around it. So that means that who is more reactive, sigma or pi bonds? Pi bonds are more reactive. Why are pi bonds more reactive? Because they are more exposed. The sigma is in the inside. The pi is in the outside. So if there is any attack, of course, the pi is the one that's going to be the first one to be attacked or to attack, right? Okay, so let's continue with these slides. The pi bond uses unhybridized p orbitals, of course, right? So this is the sp2 hybridization. You have the s orbital and the 3p orbitals. You hybridize only 2 p orbitals, forming 3 hybrids. And then you preserve that pure p orbital, right? Which can be px, py, or pz. This one is the result of the hybridization is 120 degrees apart. For the next one, I have carbon dioxide. What is the shape of carbon dioxide? 2 electron groups, 0 lone pairs, is linear. What are the bond angles? For linear is 180 degrees. This is carbon dioxide, right? So if we look at the carbon dioxide before I pass the page, here in carbon dioxide, I would say this one is a sigma bond. What would be this? This one should be a pi bond, right? The second one should be a pi. Always the first bond is going to be the sigma, and the second floor is going to be the pi. In this case, also COO, right? So one of them is going to be the sigma and the other one is going to be the pi. What is the hybridization of this carbon right here? The hybridization of this carbon is going to be sp. Why sp? Because sp allows you to have two bondings. In this case, you have two double bonds, which is exactly the idea for sp hybridization. Sp hybridization combines one s orbital and one p orbital. Right? Linear arrangement, and you have two pure p orbitals, which are needed to form the pi bonds. Okay? So here is the how it is decomposed or how is the hybridization occurring. This is what happens. You only mix one S and one P. You form two hybrids, right? These are your two hybrids. And that's how they look like together, right? 180 degrees. This is the COO. This is exactly the balloon system I drew you, right? I drew for you a few seconds ago, being with the SP2. They do it here with an SP. So here you can see that these are the hybrids. This is the SP hybrid, and this is also the SP hybrid here in yellow. The PX and the PY, or the two p orbitals, are right here. Right? One is going to be, let's label this as PX, right? It's just an example, doesn't have to be PX. And this one is going to be PY. This oxygen is also sp2, right? This one is sp, but this one is sp2 because it has three groups, three electron groups. What are the three electron groups? The three electron groups for oxygen are the lone pair, second lone pair, and the double bond. That's why it's three electron groups. Three electron groups is sp2. For carbon, it's two electron groups, this double bond and this other double bond, so sp. Okay? So here you have the oxygen forms a sigma bond with the carbon. Here's where you see the overlap, right? Right here it's a sigma bond. Also sigma bond here. Okay? And the pi bond is formed here and here with the oxygen, and the other oxygen uses the other p orbital. You cannot form a second pi bond with the same p orbital. It has to be formed with another p orbital, right? You see right here that the carbon is using this vertical p orbital, the vertical p orbital, to form the pi bond with the vertical p orbital of this oxygen. That is a pi bond right here. Now, this oxygen now also wants to form a pi bond. This oxygen right here, let me change the... This oxygen also wants to form a pi bond with the carbon, but the carbon cannot use this vertical p orbital, has to use this horizontal, let's call it horizontal p orbital. So that's why this ones I want to form a pi bond right here. Okay, so you cannot form the same pi bond, right, with two different atoms using the same p orbital. It has to be a separate. In this case, it's a second p orbital that you are using. Draw the Lewis distribution for cyanhydric acid. Which hybrid orbitals are used, right? So I think we did it, right? We did it here. In our example, here is another concept check. Determine the bond angle and expected hybridization in the central atom for each of the, let me write them, CO2 and SO2, right? So in this case, I have NH3. For NH3, if I draw it, 1, 2, 3, 4, 5, five valence electrons, hydrogen 1, nitrogen, hydrogen 1, they form a covalent bond, covalent bond, covalent bond. So in this case, nitrogen has 4 electron groups, 1, 2, 3, 4, 4 electron groups, 0 lone pairs, means that it's tetrahedral. Right? Tetrahedral is the geometry, but I have four electron groups, so that means that it's an sp3 or hybridization. Okay? So how many pi bonds? How many sigma bonds? I have all sigma, right? All sigma bonds. The geometry here is, oh my bad, it's not tetrahedral because it's one lone pair. My bad. Why did I write 0 lone pairs? I can see clearly the one lone pair. So it's trigonal pyramid, right? Trigonal pyramid because it has one lone pair. In the case of carbon dioxide, If we do the Lewis structure from chapter 8, you will get CO2. In this case, is 2 electron groups, 0 lone pairs, right? Definitely that's going to be linear. C double O, C double O, right? So here you have sigma, sigma, pi, pi. In sulfur dioxide, it would be like that, yeah. Does it have to be like this? I mean, not necessarily. I mean, that is if I make the sulfur expand the octet, right? Because definitely I can see that the sulfur is expanding the octet here, but I have the lowest number of formal charges. I don't have formal, all the formal charges are going to be 0. The other option for this could be being like this. That's the other option for sulfur dioxide. Okay. But in any case, let's look at this one. Okay? So 3 electron groups, right? 1 lone pair, that should be bent. But if we look at the 3 electron groups, means that it's an sp, sp2, sp hybridization. Well, in this case, it's different, right? Because here sulfur has an extra, expands the octet. But here, if I form sigma, sigma, pi, pi, right? If I form 2 pi's, that means that I'm in form of an sp hybridization. Okay? So let's see what happens with the NH3, 109 degrees, sp3, SO2, sp, I should say carbon dioxide. Oh, apparently they are using the hybridization, this hybridization. Okay, so I wasn't sure to which one you will form. Okay, so here they are using, because I was doing the analysis here, but apparently they are doing the analysis here. You do the analysis here, yeah, definitely. You have three electron groups, right? 3 electron groups. That means that 3 electron groups is going to be sp2 hybridization, right? And then they have 1 lone pair. And then that's exactly what you have for right? Sigma, sigma, pi. So if you form only one pi bond is sp2 hybridization. If you are able to form 2 pi bonds, is sp hybridization. If you form 0 pi bonds, is sp3 hybridization. Okay, so that would be another system, another way how to best address what type of hybridization you are facing. You form 0 pi bonds, sp3, 1 pi bond, sp2, 2 pi bonds. For example, in carbon dioxide, you're forming 2 pi bonds. For 2 pi bonds is sp hybridization. Ammonia, right? Ammonia forms 0 pi bonds. 0 pi bonds, sp3 hybridization, right? So let's continue with the, okay, using the localized model. Okay, so, okay, so now that we learned or we finished about hybridization, now we will go to another section, which is about molecular orbital, or which is called the MO. Okay, so the MO explains like how this pairing or how does this bonding occur. Okay? So, for example, the bonding, is it like, right? How can you form this sigma or this pi bond? How do these electrons match? I mean, is it that simple as putting 2 balloons or 2 orbitals, one on top of the other to form a sigma bond? Or to do a through space interaction to get a p orbital? Well, the MO model really tell us like how are the electrons placed or paired or bonded between 2 atoms according to the energy. Okay? So here is the theory about the, paragraph about the theory is the nucleus are assumed to occupy orbitals as they do in atoms. Okay, and the electrons are assumed to be delocalized rather than always located in the given pair of atoms. Okay, so the electron probability in both molecular orbitals is centered along the line passing through the 2 nuclei. Yeah, so what that means is that if you have a molecule let's say like you have here hydrogen and hydrogen. What is that dash representing? Well, that dash really represents the overlap of the two orbitals. In this case, you have two s orbitals, and then that overlap really, it represents that the electrons are moving between the two elements. Okay, so in the molecule, only the molecular orbitals are available for occupation by electrons. Yes, that's true. So whenever two elements or two atoms decide to form molecules, we're not talking about atomic orbitals anymore. Now we talk about molecular orbitals. Okay? This is how it happens. Then I think it's better if I use my screen, my camera. Okay, so let's say that I have a hydrogen, right? That has one s one electron, and the other hydrogen that has also one s one electron. These two guys, they decide to get together, right? To form a covalent bond between them. So hydrogen and hydrogen, they decide to form a bond, which is H dash H. So how does this happen, right? So each electron contributes, I mean, each hydrogen contributes with one electron. But here is the thing, like if I'm using one atomic orbital and I'm using a second atomic orbital, whenever you mix two atomic orbitals, you should always get two, because the space, I mean, the orbitals cannot be wasted. So because you have two atomic orbitals, that doesn't mean that they're gonna merge to form one MO. They have to merge into two MOs. Okay? Two atomic orbitals will give you two molecular orbitals. In this case, how do they combine? In this case, you have the s orbital. Let's say here is my s orbital. Like this is my 1s of hydrogen and the 1s of hydrogen. So they do it what we say, we call it in phase. In phase, face-to-face s orbital. And then there will be another one in which you have the shade s orbital. They call it also the 1s plus 1s, or they call it also 1s minus 1s. So when these two combine, they form a molecular orbital like this. And when these two combine, they normally represent it like this. Okay, so what's the difference between these two? Is that this one is the one that the two orbitals are face to face, they are in phase. This one's not. So they're out of phase. So they are really not completely matched. What is the purpose, or what is the reason why this process happens? The reason is that, okay, so I have one atomic orbital, I have two atomic orbitals, right? And two atomic orbitals here. I have to justify that these two elements bond. If these two bond to produce one atomic orbital with the same energy, that doesn't justify, right? In other words, you don't partner with your client. Let's say like my salary is 50K. If I'm gonna partner with somebody, right, to open a business, I'm not gonna partner with somebody to make my same 50K. No, I mean, that doesn't make sense. If working by myself, I make 50K. If I open a business with a partner, that obviously I want to make more, right? I mean, it's definitely you're gonna want to profit. Same thing happened with the atomic orbitals. If you are going to form a business, right, these two are going to make a business, which is a molecule, you have to gain something. You cannot just make a business or form a bond just to get the same energy. If I'm bonding with somebody, I want this energy to go lower. I want this molecular orbitals to go lower. For us, lower, I mean, for chemistry, lower means more stable, right? Which is, again, I don't want to form a bond just to have the same energy. If it has even more energy, that would be worse. So I want to gain something. In this case, you gain stability. So what is the only way how you can make this one lower? The only way how you can make this one lower is by making your second one higher. Okay, so this is exactly what happens. I know that to make a molecular orbital, I need to invest two atomic orbitals, right? Two atomic orbitals will produce two molecular orbitals. These are my two molecular orbitals. So the two molecular orbitals, they are identical, right? But how can I make a difference between these two? Okay, so these two are supposed to be the same energy, but it's not convenient for me to make them of the same energy. Why? Because I don't gain anything. But if I make this higher in energy and this one lower in energy, now I gain something because I'm making this orbital more stable than this, right? So if these two elements, they get together, so the energy goes down to form this MO, okay? So two atomic orbitals will definitely form two MOs, okay? Two atomic orbitals form two molecular orbitals. But what does the molecular orbital model say? The molecular model says that you are not going to make these two MOs identical. You will make one MO higher in energy and another MO lower in energy. Okay, you make two, but one is going to be high energy, and this one is going to be low in energy. Why do you do that? I do this because I need my molecular orbital to be lower in energy to make the bonding favorable. Because if you don't make it bonding favorable, the bonding will not occur. So that's exactly what happens here. So the MO, this is one is MO, which is called the bonding MO. Why is it called bonding MO? Because it's the lowest in energy. It's more stable. And this one is the anti-bonding MO. Why is it called anti-bonding? Because it's not good for bonding. It's too high in energy. So the molecular orbital will always divide into two, right? Two atomic orbitals will produce two MOs. But those two MOs will not be at the same energy. One is going to be higher, one is going to be lower. What's the reason for that? To make at least one of the MO more stable. So the most stable, I call it a bonding MO, and the other one is going to be anti-bonding MO. Anytime that you form two atomic orbitals, do they always produce those two MOs? Yes, they always produce two MOs. Two atomic orbitals produce two MOs, one lower and one higher. Okay? So whenever you place electrons, for example, in case of hydrogen, you have one electron here, one electron here. Now I have to place these two electrons from atomic orbitals in the MOs. So 1 and 2, 1 and 2. So what is the gain here? Yeah, definitely. Hydrogen will form H2. Why? Because when hydrogens invest their electrons to form a molecule, the electrons occupy an MO that is lower in energy, at least lower than the original atomic orbitals. Then is it a favorable process? Yes, it's a favorable process. Hydrogen and hydrogen will definitely do this. That's why hydrogen in nature exists as H2. You also see that O2, N2, F2. Have you ever wondered why helium exists by itself? How come I never see helium as He2? Why I never see carbon as C2? Why H2, O2, N2, F2, Cl2, Br2, I2? There are few elements that they exist in nature as diatomic molecules. Have you ever wondered why is this the reason? Why do they exist in pairs and this one exists as single? Why carbon exists by itself, C alone? Or why aluminum is alone? Or why let's say silicon also is alone? Well, the reason is explained by MOs. MOs tell you like, is it more convenient for the atom to exist as an atom or is it more convenient to exist as a molecule? At least for hydrogen, seems to work because hydrogen brings those two electrons to a lower energy level, which is more stable. Okay, so let's continue with the PowerPoint. So this one is the bonding MO and the anti-bonding MO. Here's what they represented. They represented here with a plus and a minus, but in my case, I represent it as an empty orbital and as a shaded, right? Shaded orbital, but it's really the same. It's the same idea. MO1 is lowering energy than the s orbital of free atoms, while MO is higher energy. MO2, which is the anti-bonding, is higher. Lowering energy, anti-bonding, higher energy. This is exactly what I was showing you, right? So for hydrogen 1 and hydrogen 2 in H2, hydrogen gas, right? One electron here, one electron here. There is one MO bonding. This one is the MO anti-bonding. You have two electrons here, so I fill in first the MO. Okay? DMO bonding. Right, so let's see. Oh, here is something, the anti-bonding, the labels. Um, here about the molecular electron configuration can be written in similar to atomic electron configuration. Each molecular orbital can hold 2 electrons, right, of opposite spins. What are those 2 electrons? Yeah, well, it's like filling up in the boxes that we were doing for electron configuration. So here you have to do a spin up, a spin down. You do one at a time. You always go up in energy, meaning that this MO has to be filled before the second MO. You cannot start filling MO2 without having MO1 completely filled. Okay. Okay, let's see, let's continue. The number of orbitals are conserved. What does that mean, number of orbitals are conserved? Meaning that if you are investing 2 atomic orbitals, you should also get 3 molecular orbitals. The number of orbitals are conserved. Okay? Bond order is the larger bond order, means like bond strength, the number of bonding electrons minus the number of anti-bonding electrons. Okay? So in this case, the number of bonding, this one is my my sigma bond, right? And this one is the sigma star. Sigma star means that the high energy sigma bond that I'm forming. Let me do it in a better, let's say, yeah, I'll do an example here. Okay. Let's say that they tell me write the MO of helium-2. Helium-2 is 1s2, right? So that's the electron configuration of helium. Helium is atomic number 2. So the electron configuration is 1s2. So I'm pretending that helium exists as diatomic. So helium will have 1, 2, and another helium will have 1 and 2. We're talking about the 1s, right? The 1s sublevel. So if I'm combining 2 atomic orbitals, I should also get two molecular orbitals. I do it like this, right? In the book, they do it plus plus, and then they do here plus minus, just to show that they are the opposite. Okay. Now here, what do I have? I have 4 electrons here. Okay. Once again, why do I have 2 MOs? I have 2 MOs because I'm starting with 2 atomic orbitals, right? 2 AOs. AO is atomic orbital, and then MO is molecular orbital. If I'm starting with 2 AOs, I have to finish with 2 MOs. 2 MOs, both MOs will be separated. One is the bonding, one is the anti-bonding, right? So how many electrons should I place? 1, 2, 3, 4. So I start putting 1, 2, 3, and 4. That is the penalty. I'm not supposed to put electrons in the anti-bonding. Well, in this case, I have to, because they are telling me like draw the MO orbitals or MO diagram for helium-2. So in this case, they are forcing me to draw the diagram for He2. So I have to put the electrons. So how many electrons in the bond order? Number of electrons in the bonding minus the number of electrons in the anti-bonding. Okay, divided by 2. So the bond order would be, in this case, how many electrons in my bonding? In this case, I have 2 electrons minus how many electrons in the anti-bonding? 2 electrons. 2 minus 2 divided by 2, 0 divided by 2, order 0. That means that this doesn't exist. Okay, so that's in this case is 1. That means that it forms a single bond. But here, example H2 minus, it will be 1.5. Right? So it's half of a bond. So that's not a favorable bonding. Okay, so now here, even though the bond order is 0, that means that there is no bond, that doesn't exist. That means that He and He doesn't exist. There is no helium because my bond order is 0. If I have a bond order 1, that means that hydrogen and hydrogen, they form a single bond. If I have a bond order of 2, that means that they form a double bond, like in oxygen. Okay, so in the case that let's say that they do form a chemical bond, this one will be called a sigma. and this one is called a sigma star. Okay, so the sigma means that the sigma bonding, and the sigma is a bond that is forming an anti-bonding. Obviously, you don't want electrons in a sigma star, because that means that it's going to make it unstable. Anytime that you see a sigma star or any star, that is an unfavorable process. I mean, definitely you don't want that. You want electrons in the simple bonds, right? So let's continue with the H2 minus. Yeah, here in H2 minus, you have an additional electron, right? Normally hydrogen has only one and one, and with a minus, this is telling us that you have an extra electron. That's why you have here a second electron. Why I don't have a second electron here? Because they are telling you only -1. That means that you are adding one electron. So you're adding one electron, you have to put 3 electrons, right? You can see here, 2 and 1, that means 3. So 1, 2, 3. 1, 2, 3, you have here some bonding. Here you have a sigma star, because you have electron in the anti-bonding, right, MO. And here you have 2 electrons in the bonding MO. So according to the formula for bond order, you have number of bonding, 2, -1, because I have 1 electron. All right. So let's continue. So homonuclear diatomic molecules. So here is basically the same idea. That's what we've been doing with hydrogen and helium. Homonuclear means that you're using the same elements to form the diatomic molecules, 2 identical atoms. Only the valence orbitals of the atoms contribute significantly to the molecule. So you're only supposed to use the valence electrons. Okay. Paramagnetism. What is paramagnetism and diamagnetism? So paramagnetism is a property really, in which a substance is attracted into the inducing magnetic field. Okay, so paramagnetic means that it responds to a magnetic field, and diamagnetic means that it does not respond to a magnetic field. For example, I would say in my case, this helium +2, I know that this helium doesn't exist, right? Because I had a bond order 0. But let's say that it exists. So if it exists, if they ask me, is this molecule paramagnetic or is this diamagnetic? So how do I determine if it's diamagnetic or paramagnetic? It depends on the pairing of electrons. For example, here, all my electrons are paired. If all the electrons are paired, that means that the molecule is diamagnetic. What happens if I have 1 ampere electron, at least 1? So now this one I would say is paramagnetic. So it's basically is based on the pairing. Everything is paired, diamagnetic. One of them is ampere, or 2 of them are ampere, or 3 of them are ampere, it is paramagnetic, right? Because it is the spin that has not been paired. That's what is responding to the magnetic field. Heteronuclear, in this case, you have 2 different atoms. Here we have an example for HF, right? So HF is a 2p orbital fluorine, is at a lower energy than the 1s orbital of hydrogen. Yeah, that's something very important that we need to consider for this particular chapter. So here I'll show you in my camera. Here, this one, I made a copy from the book, page 373. Obviously, this is gonna change from the book edition, but here there is a diagram. It says figures 9.38. It's about the bonding in boron, carbon, nitrogen, oxygen, and fluorine. Okay, so this is the conventional. I would say like this one is really conventional way how to write the MOS. For example, when you have oxygen, oxygen, or fluorine, fluorine, here you have the sigma 2s, 2s star. Then you have the sigma 2p, and the sigma 2p star is all the way up. And then here I have a different distribution of the bonding. See? So for boron, I have here the 2s star, pi. The pi 2p comes before the sigma 2p. That is not the case in oxygen and fluorine. In oxygen and fluorine, the sigma 2p comes before the pi 2p. That is the small difference when you are working with boron, carbon, and nitrogen. versus working with oxygen and fluorine is that these groups, these two are swapped. This is only because of the energy differences. So remember that oxygen and fluorine are on the periodic table, are all the way on the right side. So the orbitals are more electronegative. That electronegativity also creates a discrepancy or a difference in the energy. So the sigma, in this case, is lower energy than the pi. Here, the pi is lower than the sigma. Okay, so take that into consideration. Have always this handy. You don't have to memorize it, of course, even in a face-to-face, in a hybrid or any type of lecture. This one has to be provided because there is no way how we can memorize it, how the orbitals are presented or are let's say like schemes, right, or distributed in the atom. So take this into consideration. I will definitely do some problems with this using this the distribution of the elements. Okay, but in this case, HF, this is a case for heteronuclear. Electrons prefer to be closer to fluorine atom. The 2p electron of free fluorine is at the lower energy than the 1s electron. So here is the HF 1s, right, electron versus the 2p electron. So in this case, the 2p orbital is lower in energy than the 1s orbital of the hydrogen. Why is that? Well, because of the size of the atom, right? The size of F of the fluorine makes it lowering energy for the 2p. So when you do the MOS, right, it is kind of non-symmetrical. The ones that I was showing you before, okay, so that's maybe the one of the differences is that the one that I was showing you before is a perfect symmetry, right? Let's say like 2 fingers up, 2 fingers down, right? So it's a perfect symmetry. Whenever you do a, let's say, element X and element X, the difference or in let's say in the geometry is perfect. Like this distance is equal to this distance. But if you do X and Y, you cannot expect that the X and Y are going to be the same energy. Maybe the Y is going to be lower. So when you do MOS here, right, definitely it's not going to look symmetrical because they are not the same energy. You are not mixing two things. This is what happens when you have a heteronuclear MO. This is a homonuclear. Homonuclear, obviously, they're going to have the same energies. Heteronuclear, we cannot expect them to have the same energy. Even if you're mixing the same orbitals, let's say that the 2p of X might not be of the same energy of the 2p of Y, then you cannot assume that they have the same energy. Okay, so they will have a different type of energy. And actually, this one is useful because you can predict the polarity only if you know the energies, of course, right? But who is going to memorize the energies? Nobody. You have to be told in the question, like which orbital is high in energy. For example, in this particular problem, here they are telling us that the 2p electrons on a free fluorine is at lower energy than the 1s electron on a free hydrogen atom. This is part of the question. You have to be told this. So that's how you come up with this, that 2f of the fluorine is lower, right? The 2p of the fluorine is lower than the 1s of the hydrogen. Then after that, you can construct your MO. 2 atomic orbitals obviously are going to create 2 MOs. But the electrons, where are the electrons closer to? If I look at the diagram, these 2 electrons are closer to the F atom, right? Which makes sense because when you have HF, we know by electronegativity which one wins in electronegativity. Fluorine is more electronegative than hydrogen, right? There is a polarity there. So this is, the MO also explains the polarity of a bond. If a particular pair of electrons is closer to a particular element or atom of that particular bond, definitely that's the one that's going to be more electronegative, or it's going to be closer in energy to that, right? So for example, here it says, the diagram predicts that the HF molecule should be stable because both electrons are lower in energy. Yeah, they're occupying the bonding MO. Okay, so again, to the energy in the free hydrogen and fluorine atom, which is the driving force. Yes, so HF, they do form a chemical bond because the electrons are occupying a bonding, right? A bonding orbital. but also the pi molecular orbital, the pi MO, containing the electrons, shows a greater electron probability close to the fluorine. Okay? That's exactly what I was trying to tell you here, is that those two electrons are closer in energy to the 2p. Who is 2p? The 2p is fluorine. That means that those two electrons are going to be more towards the fluorine side. So the electron per electron is not shared equally, as we know in a polar bonding. And then this causes the fluorine atom to have a slight excess of negative and charge and leave the hydrogen atom partially positive, which is exactly what I was saying with the delta plus and the delta minus. This is exactly the bond polarity observed for HF. Okay? So this ends this chapter 9. There are more sections and topics on chapter 9, but I'm skipping. But once again, I'm selecting the most important aspects for this chapter. I mean, there's a lot of information about bonding and MOs and the molecular orbitals, but I would say that this is the most important. This is the substance and what I want you guys really to learn or to take with you to chemistry 2 and for the future classes as well. So it's how the atoms bond. Obviously, will be more complex systems, there will be more complex molecules, but the idea is the same. So I want you to start with these small steps, doing heteronuclear and homonuclear smaller molecules. And then after that, you can scale it up. But I think that right now we are fine by doing this heteronuclear and homonuclear using diatomic molecules. That's all, right? So please let me know if there are more questions regarding this chapter 9.